And it's now my pleasure as a long-standing organizer of Hot Interconnects, I'm Dan Pitt, to introduce our panel chair, Scott Schweitzer. And I've been involved with Hot Interconnects since about 1994, year two, I think. I think it started in 93, and I've been involved in the organization for many years. And it's really great to see how successful it is turning into an online conference this year. So our panel discussion is going to be particularly timely and exciting because we've been talking about in some of these talks how we do this low latency processing, how we use aggregated accelerators, and really how we've made accelerators sort of the fourth pillar of what goes on in a data center between compute, networking, and storage. Now we have accelerators. And Scott Schweitzer is going to be a perfect person to lead us in this, discussion of how we meet these application needs, some of which Alan mentioned, of low latency, of machine learning inference, of media processing, of even, consumer gaming, things that are happening, at the edge as well as in the core. So this is just a perfect time. So Scott Schweitzer has, been in networking a long time. He started doing things that none of us really do much anymore, which is pulling cables, those cream-colored PC network cables in the mid-1980s through the T.J. Watson Research Center at IBM in Yorktown Heights, New York. And since then, he's sold supercomputers for NEC. He's marketed HPC interconnects and 10 gigabit Ethernet for Miracom. They used to be an active participant in Hot Interconnects, and promoted SolarFlare's SmartNICs to high-frequency traders. And we've actually had quite a history with high-frequency trading and Hot Interconnects. In fact, we were hosted by Credit Suisse when we left the Bay Area, the only time in 2009. Today, Scott is the technology evangelist on Xilinx's system architecture team, where he is driving the use of acceleration technology in the data center. So hand it over to Scott. Please give him a welcome and enjoy the panel. And thank you, Scott, for pulling it together.
Thanks, Dan. I appreciate that. So today, folks, I want to thank everybody for attending. During our panel introductions, I'll show a couple slides, one for each of the panelists. They'll have about 2 minutes to kind of go over their position in the market, what they're up to. I'm going to kind of hold you all to the 2-minute mark so that way we don't get too carried away. Following that, I've got 13 questions of my own. We have the Slack channel open, so folks may be posting to that as well. None of the participants on the call have seen or heard of these questions, so it's a live event. It's going to be a little surprising here and there, hopefully, and we'll have something that should be interesting and compelling for people to follow. And also won't be a marketing pitch for the whole time that we're going to be on. I run the questions by other folks in the industry that I've worked with over the last 2 decades, and I think they'll be pretty appropriate, and they seem to be compelling and things that we're all interested in. I'm going to try and stay away from using the term SmartNIC so I don't color the conversation or DPU or even IPU, and at the end we'll wrap it up and see what everybody thinks. Today I'm honored to have 5 folks that really know the technology and have been in this for years, decades like myself. So I think we should probably just jump right in and get started. I'm going to go in company order for the introductions. And so the first one out of the gate is going to be Andy. Andy Gospodarek. Hope I got that right, Andy. Thanks. He's the architect and open sorcerer at Broadcom. He's the software guy on the panel with 20 years of professional networking experience. The past 4 years, he's been a Linux kernel developer and software architect at Broadcom, focused on high-performance networking, including XDP, DPDK, hardware offloads, x86 and ARMv8 architectures. Before that, he spent 2 years as a member of the technical staff at Cumulus Networks, which is now part of Mellanox, or I should say NVIDIA. And prior to that, 8 years at Red Hat in various engineering roles. Andy, it's a pleasure to have you here today. Why don't you tell us a little bit about yourself and what Broadcom's up to? And let me see if I can share a screen. There we go. Share that one. And is that working for everybody?
Yeah, I can see it. Thanks so much. Thanks for having me. So yeah, I'm here today to talk, about our Stingray. I won't say SmartNIC card in particular. you know, sometimes we call it an SoC, sometimes we think about it as a NIC in particular, but it's a pretty cool piece of hardware in my opinion. One of the biggest things I like about it is that it's an open platform. So we have the opportunity to use fairly common architecture. It's got 8 ARM cores on it, A72s at 3 gigahertz. And it really gives us a chance to allow people to build solutions around it, software-based if they like, or the TrueFlow flow management infrastructure and hardware that we have on it allows people to be able to offload and accelerate applications really nicely. So it's probably not quite the balance of my 2 minutes, but I'll save some of my talking for the good questions later.
Thanks, Andy. I appreciate that. The next person we have on the team is Pradeep Sinhu. Pradeep, he's been around forever. He's the CEO over at Fungible Networks. Yesterday, his company Fungible came out of stealth mode at Hot Chips. I'm sure he's extremely excited to talk to all of us. So Pradeep, we're going to keep you to 2 minutes because I know you're going to try to run long. Pradeep is the CEO and founder of Fungible, as I mentioned already, a Santa Clara-based startup providing scale and next-generation solutions for the data center, cloud, and IT industries. Before Fungible, he co-founded Juniper Networks, where he served as its CTO. Prior to Juniper, he was a principal scientist and distinguished engineer at the Computer Science Center at Xerox's Palo Alto Research Center. Everybody knows it as PARC. And he pushed the envelope on what silicon could do for networking and processing. Please welcome Pradeep.
Thank you very much. Can you hear me well?
Yes, we can.
Excellent. Well, thank you for having me on the panel. As you mentioned, I'm a co-founder and CEO at Fungible. And we're very excited to talk about the DPU, which we believe is a new category of microprocessor for data centers, particularly data centers built on the principles of scale out. Like Andy, we will not call ourselves SmartNICs because we do a lot more. And you know, the 2 problems that we set out to solve, it's very important for me to outline those. And these are problems that are endemic in data centers today. The first is that it's the node-to-node interaction over a network is very inefficient. And this inefficiency prevents you from building disaggregated scale-out infrastructure. And the second problem is that there's this class of computations which are relatively new, relatively meaning the last 5 to 10 years have been getting more and more important. These computations we call data-centric. And the DPU is designed to implement and execute these data-centric computations some 10 to 20 times faster than general purpose CPUs. And we combine the capabilities of True Fabric, which solves the first problem of node-to-node interactions efficiently. And the second, which is the ability to do these data-centric computations, we combine them in one device. And we believe that it is critical to have those 2 functions implemented as silicon. And more than that, we make these capabilities available in a fully programmable way. So the same thing that Andy mentioned about his device, ours is an open device, which means that people can program it to add functionality over time.
Thanks, Pradeep. I appreciate that. Next, let's move on to Michael Kagan from NVIDIA. Michael is the CTO over there at NVIDIA. He's been with Mellanox since the inception, I think, back in 1999, where he was initially the VP of Architecture, and then for the past 11 years as CTO and VP of Architecture. He's witnessed the emergence of Mellanox as a leading InfiniBand player. In fact, he and I were on opposite sides of the marketplace battle. I was promoting Miracom, he was pushing InfiniBand. InfiniBand obviously won and won the day. Today, it's the default HPC cluster interconnect. Along the way, Michael's had to make some pretty tough calls, you know, while extending their efforts into switching and the NIC business into the Ethernet, Ethernet into the data center. Recently, they've been acquired by NVIDIA. Please welcome Michael Kagan. Michael? Maybe
the word about Bluefield, which is our version of SmartNIC or DPU. Basically, the core of this technology and our competitive advantage is the NIC that is integrated there. ARM course is pretty much a commodity. Everyone can buy or build his own, but the NIC that is part of the Bluefield is the leading high-performance network adapter that actually deployed in pretty much most of the data centers across the world. It's in Azure, it's in Alibaba, in China, and more. And that's what the key advantage of our technology. So we deliver the full segregation of infrastructure computing platform and application computing platform. We have some additional accelerators, side accelerators for regular expressions and security. And that's about it.
Well, thank you, Michael. Appreciate that. The next speaker is from Pensando. Pensando is the other new NIC player in the space, smart NIC player, excuse me, intelligent NIC player in the space. We have Vipin Jain. Vipin is a CTO over at Pensando, but he's an engineer at heart, and he's one of the co-founders. He's worked on building an array of successful products and solutions during the past 20 years in infrastructure space. He's an expert in ASIC and data path, networking, distributed systems, management software, cloud infrastructure, and cloud native applications. Please welcome Vipin.
Thanks, Scott. Can you guys hear me okay?
Yes, we can.
Okay, awesome. I'll start off with, some of the things that we hear from the users, and we are definitely a startup, so we started to look at what are the challenges to solve and how to look at it disruptively. First thing we hear really is that, people want infrastructure builders really want architectural simplification in deploying infrastructure services. Second thing that we hear is like they seek more processing for less power consumption, which means cost savings both on capex opex. So more for less. It's a very common theme. The third thing that we hear is something that has to be super easy to use, can be too complicated. And the last one is some users like the technology, but they just want everything that is working end to end. So I'll just walk backwards and start describing what we are working on. So to cater to the users who are wanting production-ready end-to-end solution, we have built a scale-out management control plane. It's a pure software that could run even in public cloud that manages services in thousands of these nodes simultaneously and going higher on the scale. And for people who want to consume just the card and technology, but still want ease of use, they can use production-tested data path software with gRPC APIs right out of the card. But for the users who seek to build their own data plane IO pipelines, we have built the compiler and associated tools to get there. Now coming to this whole question of like raw power and capacity, and that's been quite a theme, especially with the Hot Chips conference. So we published a paper. I won't bore you with all the details, but we built basically a P4 substrate that can process up to 280 billion instructions per second with a very attractive power envelope of like 25 watts at 100 gig and 50 watts at 200 gig, of course, with a few microsecond latencies. And you can find the details in the paper that Francis and Mike presented at Hot Chips yesterday, with all features turned on simultaneously. And the last one is bring everything together so that the architecture becomes simpler and the failure domain is smaller. Networking, storage, visibility, security, RDMA, networking, all these functions at one place at millions of scale. All these are very highly stateful functions turned on simultaneously without impacting applications.
Thank you, Vipin. Appreciate that. The final panelist that we have today is from Xilinx, Gordon Brebner. Gordon is a Xilinx fellow on the CTO staff. He's been a researcher and innovator, bridging theory and practice to transform the hard and soft architecture of communications and computing systems. As I mentioned, Gordon is a Xilinx fellow on the CTO staff, and he joined Xilinx back in 2002, coming from the University of Edinburgh, where he was professor for a decade plus before that. Welcome, Gordon. Gordon, I saw you on there
Gordon,
earlier.
you're muted. I think.
Yeah, I was, sorry about that. After seeing all the warnings about non-muting, I did.
No worries.
So thanks for the introduction, Scott. Hello, everybody. Yeah, I'm in the CTO office. I thought I'd disgrace myself by coming with a nakedly marketing slide here. So everyone else has block diagrams and pictures. And my glib FPGA guy answer would be, we can implement any of your architectures using our FPGA. That's the slick answer. But really was to make the point of more to focus on the characteristics rather than the actual product. As people know, Xilinx is an FPGA company traditionally, but is kind of getting into the board business with the Alveo family of boards, and in particular, that's a custom version of that for SmartNIC. SmartNIC is a pejorative term. Internally, I was trying for a time to talk about SmartNAC, for Smart Network Acceleration Card, just to kind of de-stress the CPU interface, since really my point here is we want kind of line rate performance, but look at coupling that to streaming applications where you've got data streaming on and off the network, and your real-time low latency applications. My secret wish is, cut the CPU out except for emergencies, and we can have compute acceleration, which FPGAs have been known for, but coupling that directly into the network. So the kind of three aspects I'm tracing here is we want to go at line rate performance, and say FPGAs have state-of-the-art SerDes, and we can get this kind of bandwidth in and out, but then the issue is what to do with it. So repurposing the hardware, so we don't have a fixed hardware architecture. The Xilinx SmartNIC has a kind of wide pipeline architecture, which is sort of FPGA friendly, rather than lots of cores. We have some cores, but not many cores. And having domain-specific programming language, in particular, we have a P4 programming flow for the data plane of the SmartNIC, which kind of makes it open-ended. And then finally, cross-coupling this across to mainstream acceleration, what I'm calling the data fire hose handling. So the kind of aim is, we can do memory-to-memory stuff and PCIe stuff and fit in with CPUs and GPUs, but in a more native model, we're looking at data streaming in and out, and the lowest latency possible, and actually doing work on the payload as well as just this header manipulation. So that's SmartNAC, Network Acceleration Card.
Thanks, Gordon. Appreciate that intro. Now we're going to get into the non-marketing hype part of the panel discussion. I'm going to ask you guys some questions, and I'm going to kind of call on different people so I can jump around and keep it mixed up a little bit and keep it a little more lively. So we'll start this right off. Some might say that the dawn of the programmable NIC can be traced back to 3Com's delivery of a TOE with security features nearly 2 decades ago for gigabit Ethernet. Others might say that this is a fairly new category of NIC. But more importantly, what 3 features would you say define a programmable NIC in making it either smart or classifying it as a DPU or IPU? And again, let's try and keep our answers to, a minute, 2 minutes at most. Let's start with Michael from NVIDIA. Michael?
Well, my take is on this is that it basically is computer in front of computer, which is a different computing domain than the host, and it can supervise or oversee everything that's going on between the host and I/O in general and the network in particular, and can be a platform to implement the infrastructure protection, security, and the like. Of course, it needs to have right hardware accelerators, but the key thing is that it's real computer in front of computer.
Excellent. Thanks, Michael. Let's go to Pradeep over Fungible. What are your thoughts, Pradeep?
Scott, my thoughts are, I wouldn't characterize SmartNICs. I'll let others do that. I will just simply point out that there's a need in data centers for a new processing element. And this new processing element has to have 3 attributes to it. Number 1 is to execute what we call data-centric computations at least 10 to 20 times more efficiently than a general purpose CPU, which includes ARM and x86. Okay, so just putting ARM cores inside a chip doesn't solve the problem. Second is that it has to integrate what we call true fabric capabilities. The term fabric has been utterly bastardized in the industry to the point where it has no meaning whatsoever. And the fact is that to build scale out data centers, one needs the properties of a fabric, which means full cross-sectional bandwidth from small scales to large, end-to-end congestion control, error control, very low latency, very low jitter, security, and a whole bunch of, and very high levels of reliability. I would assert that despite some of the statements that have been made, 90+% of the deployments use TCP/IP as the fabric. And we all know what the issues with TCP are, that at relatively modest performance, there's no problem. But today we're at 100, 200, 400 gig. And at these levels of performance, you're chewing up a third of your cores in x86, just executing, shoveling packets back and forth. It gets pretty boring. And the last thing is that you require these functions not as a hardware pipeline. You require these functions in a fully programmable data path. And I think the key question in front of us is, what is the right approach to address this combination of flexibility and horsepower? And at a high level, lots of people are going to try different approaches, some more hardwired, some less hardwired, whether it's FPGAs or other approaches. Our approach is to combine very, very powerful general purpose CPUs intimately with a set of accelerators. And intimately means there's very, very fine-grained interactions on the chip where a procedure call either to another CPU or to another accelerator costs a mere 30 nanoseconds. And so I think it's with this kind of architectural innovation that we can solve the 2 key problems that I mentioned. It's not with marketing gimmicks or terms like SmartNIC or dumb NIC or whatever NIC you want to say. It's with solving the actual fundamental problems in front of us. And that's what we believe we've done.
Thanks, Pradeep. How about Gordon? What are your thoughts on this?
So I think for my 3, I'd certainly go along with Michael, in terms of it being a compute capability. And the critical thing is, it's genuinely offloading things that were formerly done, on a mainstream, CPU. So having that and programmability, so it's not just a collection of accelerators, but it's also in some way programmable is kind of critical to the smartness. The extra thing I'd throw in, which I think would reflect an evolution of the SmartNIC, is thinking of it as a switch. So, when you're just thinking network being connected to CPU, it's this kind of linear thing, between the network and a CPU, and that's how NIC started. But looking, not just at what Xilinx is doing, but what others are doing, is really turning into more of a little switch. So you might have 2, maybe more ports, coming in, but also it's not just going to like a CPU. Have GPUs attached, or FPGA accelerators attached. So I think traditionally switches and NICs are seen as 2 different categories, but you're seeing kind of little switches creeping into NICs as well, and I'd see that as part of the smartness, for the future.
Excellent. Thank you very much, Gordon. Appreciate that. Let's get back to Andy. Andy, what are your thoughts as a software guy?
Sure. Well, unsurprisingly, too, I also agree a lot with Michael. One of his colleagues and I worked on a presentation at IETF last year. It seems like a decade ago, but apparently it was only last year, where we really tried to define the different classifications of NIC, or think about what's happening with NICs today. And one of the things that I see as critical towards thinking of a more featureful NIC is that not only can data plane be offloaded to the NIC or to specialized hardware, but you have the opportunity to offload control plane as well. And I think that's where, when you can do both of those things, is when you start to see a really significant savings in terms of core usage or other things like that, where you can free up your server, as I like to say, to do useful work. So the control plane and data plane offload both, I think, is really important. I think another key component that's very important for a functioning device like this, I see I'm doing my best not to say any of the names, is to really have
I just didn't want to taint it.
Yeah, have the ability to shortcut the ARM core, in our case, ARM cores and other cores in other places, shortcut that processing via accelerators. And whether this is storage acceleration or network acceleration, I think that's critically important, because if a flow or a storage action can be validated, then it's very easy to have your hardware that's good at doing hardware things do that stuff. And then for me, obviously from my software perspective, and you look at my track record and my resume, the things that I've done the most over the years are work on open source. And I find open source and open platforms to be critically important. So for me, I think the opportunity to have your NIC run whatever you want. And maybe that might mean developing to an SDK, or it might be that someone could take a device and do whatever they want to with it. And they don't need to call me to ask for more features or call other people at an individual NIC provider. That most of those features that they want, if not all of them, are available from day one or very quickly.
Excellent. Thanks, Andy. Vipin, I haven't forgot you, buddy.
Okay.
What are your
Okay,
thoughts on this one?
So, I mean, we call SmartNIC, what is a SmartNIC? Something that has its own brain. I didn't coin the term, but I'm just thinking like, what is that brain? Something that can allow people to have this device have its own life, independent of the server that it is connected with, or potentially the entity it is controlling. It gives people a network-based or cloud-based manageability. That is the main power of so-called smart device like that. So something that has its own brain, number one. Second thing, I think a lot of people touched upon it, not touch any general purpose CPU, do 100% of all application IO processing in data path. And I mean implement TCP stack, I mean doing NVMe over TCP, I mean terminating like TCP connections, everything in data path. And that's what is really defining this entity to be what we call a domain specific. Otherwise, we are like, still doing some acceleration and using it with general purpose processors and doing, handoff is what really costs, anytime there's a context switch that costs a lot. So I think that whole domain specificness needs to be measured up to its trueness by ensuring that nothing really gets to the ARM cores for any kinds of functions. I'm talking like, doing TLS proxy, implementing service mesh, Istio like service mesh, those kind of things. So that's like an attribute that needs to be there so that we can truly call it domain specific. And the last thing is really for things that you have to really, use general purpose processors and all that, it should be for management, like, where do I call my gRPC into it? That's not going to go into maybe, the data plane, but the actual data path traffic needs to be there. But the Tango for terminating connections and all that, can we achieve, let's say, 1 million connections for one ARM core, those kind of things, will really bring that 20x thing that Pradeep was talking about, will bring really that 30x thing that we want to get to.
Excellent. Well, I appreciate that, Vipin. Very thoughtful. This, I'm going to kind of take this a little bit further down the same path to some degree. We were on a call yesterday with some senior folks at AMD, and they mentioned a rule of thumb of 1 gigabit per second of traffic per core, which obviously, in our businesses could be as many as 1.5 million packets per second each way for traditional x86 cores. Maybe this is how they justify 64 cores per CPU or 128 cores for dual socket system. Are you guys familiar with this? 1 gigabit per host CPU core? Do you think it's an accurate metric? Do you believe that this kind of strikes at the core of why programmable NICs are starting to become more relevant? And
Scott, let me try to address that. There is no kind of golden rule like that. I will tell you what I believe is that because of the way in which scale out has taken off, and because of the way in which people write modern programs, which is a microservices-based approach, there's been the ratio of compute-centric to data-centric has gone down, or in other words, there's a lot more east-west data traffic than there used to be. Probably a factor of 10, factor of 20, and it's only going to increase as scale out becomes pervasive. And so I don't think there's any such rule of thumb. But what is important, and somebody mentioned earlier, I think two of the panelists mentioned that we should think of this category of device as a computer in front of a computer. I think that's accurate, but it's really important to figure out, well, what computations does this thing need to perform? And at Fungible, what we did was we went back to basic principles and asked the question, okay, so what are these computations that are different than what general purpose CPUs can do? And somebody mentioned the term multiplexing. You know, CPUs are terrible at being multiplexed, okay? One of the main things you have to do to provide the right solution is to actually handle very, very heavily multiplexed stateful applications extraordinarily efficiently. General purpose CPUs can't do that. And they will never be able to do that because their main job is to execute single-threaded computations very fast. So it's actually a tension which is pulling in two different directions, which is why we thought that a new category of device is required.
Understood. Thanks, Pradeep. Vipin, I'm going to toss it back to you, buddy. What are your thoughts?
I mean, 1 gig per core, definitely arguable. People are actually doing more than that. It depends on the generation of processor and you know, it depends on a lot of factors, what software you're using, what applications you are using to test it and all that. I will go back to the comment on what kind of problems we are trying to solve. If you go back to the domain of IO processing, it's not just packet processing. It is about processing the messages. It's about processing the data inside those things. Like, can I glean my iSCSI latency numbers and draw histograms right in data paths, those kind of things. So ultimately, if we can get 50x advantage to that, 40x advantage to those kind of things, which we are good at, and it will become more and more eminent as the general purpose processors starts to show their saturation, is to and the need for compute is not going to go less per se, just because Moore's law is coming to somewhat of a saturation. People are not going to say, oh, now that I have to live with less. So trying to do more means you have to understand the domain really well, what that processing really needs. I mean, what kind of state store is needed by distributed databases, and then trying to build grounds up a pipeline and a solution that caters to those kind of things would really gain that, 1 gig, 10 gig, you name it. I mean, it can easily handle, like I said, we have demonstrated 1 million connections per second just using one ARM core. Now, is that possible? Well, not really. I mean, but then that's where the domain specific thing needs to come in. But to process 1 million connections on a standard core, it'll take long because each connection is a different one. There's context switch, there is cache misses going on and all that. And that's where I think we are thinking how to really get into that domain specific architecture.
Thanks, Vipin. Very, very insightful. Thank you. Andy, as a software guy, what are your thoughts?
Well, I think that, that number is extremely low. I mean, I think if you're comfortable living in that world and that's the number that's good enough for you, then maybe that's great, but I don't think I would be in any way happy with that number. And I think that some of those numbers it comes down to what you're using your system for. I mean, if you're in a situation where you have an extremely general purpose application load and you're trying to spread that out amongst a whole bunch of different classes of workloads in a data center, then maybe that number's okay. But if I were designing something to be very network centric, I might choose to use something like TBDK, or I might choose something to use XTP because those things are going to blow everybody else away in terms of the ability to process packets. Then again, the downside to that is that not some of those frameworks don't have the full suite or full stack that you might want. So I think I've heard, stated in a similar way, rather than, 1.5 gigabits per core. I think I can't remember the exact value now, but it's like, a relationship between the amount of memory that a system needs and the megahertz or gigahertz of a processor and the bytes of data that you want to pass. And the 1.5 might be a reasonable estimate based on core speed, but I I don't think anybody should settle for that, I guess would be what I would say.
Understood. Thanks, Andy. Michael, I didn't forget you. Where are you weighing in on this? Michael, you're on mute.
Okay, so I think that network needs to take care of the network processing on its own. So for this type of processing, it should be 0 core for infinite number of gigabits. The CPU needs to deal with the application higher level processing and not with the networking. That's the ideal case. Of course, there are some, we are in some distance of this ideal, and not all the transports are accelerated. The TCP offload basically never took off. Rocky works fine, including the encryption, and I think that whatever goes above that, we can argue whether it's network related, which is core per gigabit, or core per something else, which is the application processing.
Okay. Well, thanks, Michael. Gordon, I haven't forgot you, buddy. Where do you weigh in?
Yeah. I thought I might be.
You were probably on the same call yesterday.
Say again?
You were probably on that same call yesterday with AMD. What are your thoughts?
Yeah. Well, at first I might have less to say because I'm not pushing kind of multi-cores, etc. But I think having a measure like that actually is dumb NIC thinking, because it is kind of suggesting, the NIC is just doing some fixed set of standard functions, and then we can start making statements whether we agree or not with this. I mean, what I see inside a SmartNIC is not just, there might be some variability due to levels of sophistication, but also I see a SmartNIC as a kind of filtering device, if you like. So, at the blunt end of the network interface, you might be having to go flat out. You've got to look at every packet and deal with it. If there's some genuine richness to the smartness, then you filter some stuff in the front line, and then you could talk about a lower packet rate. If you're doing some more sophisticated functions, take for example, doing intrusion detection with TLS or something like that, you may only be checking a small number of packets, so you don't need to go flat out in that piece. So if you think of the SmartNIC as being this more heterogeneous collection of functions, it's kind of meaningless almost to me to talk about, how many gigabits can a core handle. It's more, how much does a particular core, a particular accelerator need to handle? And the interest of the SmartNIC is you're coupling these things together, and that's actually the hard part.
Okay, thanks, I appreciate that. Now I'm going to go to the opposite end of the spectrum, right? Today, packets entering, programmable NICs can be steered obviously using dedicated classifiers like Broadcom's TrueFlow, programmable logic in the form of FPGAs, general purpose ARM or MIPS cores. The problem is that as we move to 100 gig and 400 gig beyond that, the rates for single ports explode from 150 million to 600 million theoretical in each direction. How do you view your architectures, your individual architectures, being able to scale to meet these enormous rates? And let's go with Vipin first.
Okay. Yeah, thanks, Scott. We think that's where this is going to go eventually, not just 200 gig, but maybe 400 gig and higher, at a per server level, or maybe, a few cluster servers. So we think that, our architecture has a general purpose array of processing pipelines. It's not like we have 2 stages, 4 stages, or something like that. Like we are talking about literally 32 stages to 64 stages of individual processing engines with massively parallel amount of threads that could handle all this traffic. Even though a single thread can handle line rate too, but still doing that. So the main advantage that comes from doing it this way is completely software defined. So today it is X, tomorrow it's Y. Like for example, implementing NVMe over TCP in my data path pipeline as a program, not really as a fixed function, is where I think we can say that yes, it can handle not just line rate but complexity as well. And with the software defined way of using the pipeline that comes there. I'll end my comment with just one sentence, which is that, you know, the benefit comes from the fact that you go beyond layer 4s and all that, but it comes from the fact that you don't leave the cache pipeline while you are processing a given packet, and that could become a message. So you may be collecting all those packets to form a message to terminate a TCP connection, but still, while you are processing a message, while you are doing TCP sequencing, while you're determining what TLS session this particular thing belongs to, you are literally doing it the fastest possible way, because you're not missing a single cache, hit, both from instruction and the data point of view. And that's why you are able to do like 200 gig or 400 gig worth of performance, at least in the way we have seen it.
Thanks, Vipin. Let's go back to Andy. Andy, what are your thoughts?
I think if you look at the last 4 years of hardware development that we've done at Broadcom, and you mentioned the TrueFlow offload engine, I think we've seen basically a more or less 4 to 5x improvement in terms of the total number of packets per second that can be processed by that hardware. So I think that's an important number, and I think that realistically, people do want to talk about packets per second, and they think it's critical. I will say that in my time dealing with users and dealing with customers, that there are a very limited number of people, and this might not be a great thing to say, but I think it's true. There are a very limited number of people that are actually concerned with hitting that maximum line rate packets with the smallest possible packets. So while I think finding a case where we can hit line rate at 200, 400, whatever speed you want, I don't think it's realistic that many people are actually doing that. And I'm sure someone on this panel will tell me otherwise, but I just don't see it based on the customers I've interacted with and the users I've interacted with over time, that in the data center, you probably are not in a situation where you're going to need that much.
Okay. Michael, what are your thoughts?
Yeah, I would agree with Andy in terms of, there's a 80 byte is the minimum packet size on the Ethernet layer 2, but there is no much packets like this in the data center, thanks for more complex transports and overall networks and the like. So our goal has been so far, and we met this goal, to run stuff at line rate. Our latest devices is 200 gig, and we are pretty much meeting this goal. And so far so good, and we are looking forward to do it the same at the higher rates.
Thank you, Michael. Appreciate that. Pradeep, where do you stand on this?
Scott, so I think one can get lost here, looking at the trees instead of the forest. And what I would say is, let's ask the question why we are here, okay? We're here because Moore's law is flattening, okay? I can tell you that if I were able to build a general purpose CPU at 1 trillion hertz, we would not be having this panel discussion at all, okay? We're having this discussion because we know that CMOS the curves are flattening, performance is not doubling. I would by far actually want to write programs on a completely general purpose CPU if it was possible. It's not possible anymore. If you look at, the way to look at this, I think, is that you start with bits coming in on a wire, and the computation that you're doing has a shape of a pyramid where they become more and more and more complex and more stateful. And it's not black and white. It's actually a continuum. And the entire debate that the industry is happening is, where does the continuum end inside a device that is interfacing with the network? And where does general purpose processing start in an x86 or ARM? And the point I would leave you with, is that I think the correct interface is not TCP send and receive. Okay, it's way too low level. It's not RDMA reads and writes, again, too low level. A modern proper interface is something like gRPC. Well, if you look at the number of layers in gRPC, let me count them for you. Ethernet, IP, TCP, TLS, HTTPS, JSON, protobus, okay? All of that gobbledygook is done in software today. And it can be done much, much more efficiently on an engine which is custom built for this. This is what's happening. So we need to recognize what are these basic computations that general purpose CPUs don't do well because of their inherent architecture. We need to have architectural innovation to address these in a much more efficient way, because scale out is here to stay, okay? There's nothing else for the next 5, 10 years. Maybe somebody will invent quantum computing and then we'll have another job. But in the meantime, scale out is here to stay, and we got to address the problems that we have right now.
Excellent. Well, thanks, Pradeep. Gordon, I didn't forget you.
Yep, never forgotten. Yeah, I think in terms of scaling, one interesting thing, about being an FPGA company, doing FPGA chips rather than NIC chips, is we have tons of high-speed I/O around about like bits of I/O available on the device, and then the question is, can you actually handle it with some kind of architecture on the FPGA? And a couple of years ago, I had a colleague who was entering a DARPA project, for optical multi-terabit stuff, and he said, what's the point if you can't handle it? So this is a kind of challenge we face, and we're less thinking in terms of your cores and your restrictions on cores and communication between cores, but in our case, like wide data paths, etc. And a few years ago, I had a kind of little personal thesis. 100 gig was the kind of maximum we could get to, with one wide pipeline, and then things would break down the way we're doing it. It turned out actually that was an incorrect thesis, because both the silicon helped, and also we figured out how to do 400 gig. So yeah, I think in terms of a multi-core style architecture, we can see how the current way of doing things can scale up to this terabit range. Our standard solution is it doesn't go fast enough. So we have the capability, but the real challenge is fitting the kind of price point for a smart NIC, which is a different issue, because we can get big enough FPGAs to do terabit stuff today, but no one's going to buy it for a smart NIC purpose. So we have to remember the cost of doing things as well as the interesting stuff, the technology and the architecture.
Excellent. Thanks, Gordon. I'm actually going to jump to one of the Slack questions because we have a bunch of people chiming in with stuff. This one's from Tyler Jowers. CPUs have flow control in the form of branching because they can cache instructions and data better. So where does a DPU or SmartNIC land in between processing speed versus flow control? And let's go, Michael. For that one. You first.
I'm not sure I understand the question. What's the flow control on the DPU?
Yeah, they're basically saying that since DPUs and SmartNICs are using their own architectures for things, how do they fit in when compared against a CPU that can obviously cache instructions and manage data more efficiently? I don't know. That's.
Well, I sort of agree with half of the statement and disagree with other half. Okay, I do agree that CPU has the caches, but I don't agree that they manage data efficiently. So, well, the way we implement our it's in our NICs is that there is a dedicated hardware engines for whatever task is needed. Like you can think about this as the sort of equivalent of TCAM to make the decisions. And now the way it's particularly implemented is we do have a caches, by the way, and they are serving the engines that are supposed to process the data. It's caches basically caching the context, and that's the way it works. Okay. So I'm not sure how it's related to flow control, but
yeah,
Scott, may I attempt to answer that question?
I was going to throw it right to you anyway, Pradeep. Go ahead.
Thank you. I think the gentleman who asked the question intended to use the term control flow and not flow control. I know that those terms sound the same. I think what he meant was, hey, the control flow in CPUs because their capability to branch and do procedure calls and so on is quite general. It's absolutely true, okay? But caches and so on and so forth don't perform very well for this class of problems. Now, what we've done in the DPU is we've taken this classical concept of control flow, which is a procedure call, and we've generalized it to a concept which has been known for a long time called continuations. Continuations are the most general form of control flow. Procedure calls are a subset of that. In particular, what continuations allow you to do is they allow you to do call continue instead of call return. And what call continue allows you to do is to build arbitrarily general pipelines of units that are connected together, where each unit is executing a small number of instructions, and you have a chain, dynamic chain of accelerator threads and general purpose threads. So for the problem that we're talking about, which is data-centric computing, we believe we have the most efficient and general architecture. And at the end of the day, it's not about how fast you go or how general you are. You need to provide both. And if you don't provide both, you won't be successful.
Understood. Andy, what do you think from a software point of view with respect to control flow?
So I think, kind of like Michael, I had a little bit of struggle to really fully understand the question. I'm actually alt-tabbing back to look at the question on Slack. Because I think it's, I think in the sense of the Broadcom hardware, for example, right, we have these ARM cores doing some work, and we have our TrueFlow engine doing some work as well. So, in that sense, speed versus the control to move things back and forth. The pipeline is in a sense, from a speed standpoint, fairly fixed. And so you're going to get that maximum performance wherever you can. I hate to say it, I wish I had a better way to answer the question, but I think I'm still struggling to understand what what Tyler was hoping to ask there. So I'm sorry.
Understand, no worries. Gordon, what do you think?
Yeah. Flow control to us has one meaning, control flow, something completely different.
Entirely different concept.
I think, in my kind of pipeline world, the people think, well, these control flow things don't come into it. But of course they do as soon as you have any degree of sophistication. If it's a kind of dumb pipeline in a dumb NIC, then you can just pump stuff through. But although we might not have, layers of caching, etc. We also have different layers of memory at different rates and things. And there's many how you look. Well, we do predictive things. If you're waiting for a lookup to happen, you can do some guesswork sometimes. So it's not just a control flow problem. As one would see, in executing a program kind of thing, in kind of very hardware-like pipeline implementations, you have these kind of uncertainties, and if you're trying to minimize latency, you do want to take shortcuts and things. So these kind of control flow issues, prediction, are very relevant in the hardware world. It's not just for software.
Okay. Well, there have been several different questions that have come up on Slack.
Scott, do you want me to take on that one?
Oh yeah, I'm sorry, Vipin. I thought
no, I was patiently waiting. No, because
I know you were. I'm sorry. I'm like checking off as people talk, and
Hey, Vipin, you've never been shy before, man. Come on, jump in.
Jump right in. Go ahead, buddy.
Yeah, so I think it's a very, very good question. It goes back to the problem of, like, if we are trying to offload what a general purpose processor can do, how can we deal with it in a NIC kind of function wherein you process packet by packet at a time? And that's why you can do line rate, because the only thing you do is fix function that a packet does. But a general purpose processor has a different control flow, because something needs to execute, then it goes to sleep, and then something happens and all that. So let me take an example of how we implemented TCP stack in the data path pipeline to describe why this could be done without running into any of these control flow problems whatsoever. So first thing is that we have to move away from this packet processing completely out. We are not processing IP TCP packets. We are processing really a meaningful message that is going around that, which means what you need inside the nuts and bolts of your devices is run to completion model. You can't say that I have X number of instructions to process this packet, and after that I'm done, and this packet needs to move on because I have something else which is coming up, and cache needs to be filled in with that. So so run to completion, doing memory access in the in my instruction sets. Memory access being like DMA memory access, not really the the other ones where you just read memory and write memory, and doing timer functions. With these 3-4 basic instructions in our deep a data processing unit or a SmartNIC or a distributed service card, you can achieve the goodness of building a general purpose programs without running into the disadvantage of so-called the control flow, largely because you're still processing one message at a time and then saving it in either memory or keeping it out. As long as you have the NOC bandwidth, which we call network interconnect bandwidth, that can deal with this capacity, you should be good to go. And I think we are doing it, including implementing TCP timers. And literally we took those functions of TCP stack and implemented that. So it is a general purpose program, except that now it is running in the data path.
Okay, thank you. Another one we're going to harvest kind of from Slack, and it runs parallel with one of the ones I had. You've each chose some sort of computational architecture, obviously, to address moving packets and processing packets. Some of you guys have FPGAs, some of you guys have ARM cores, some folks use MIPS64. There's RISC-V out there that it doesn't appear anybody's picked up on, at least not for SmartNICs. Why did you pick the particular computational unit you did? And let's try and not to get too overboard on an explanation, but give us kind of a quickie as to why you picked that architecture as opposed to one of the other ones that might be out there. And Vipin, since I ignored you last time, you get to go first this time.
Sure. I mean, it's all about ecosystem. You have to look at, where the tooling is highly available. If I think there was a comment made by Andy on openness and open ecosystem, and it's very apt because you have to appeal to people who are building these, massive infrastructure using widely available tooling, using widely available, resources, and the most primary factor in that decision really is like which one is equipped with all the relevant tooling, and that's our main reason to go with what we did. Okay,
and you guys went with ARM, correct?
Yes, we went with ARM. ARM is quite rich on the ecosystem. I can definitely say that.
Now I know Pradeep is probably jumping out of his skin to get in on this. And
do I look like I'm jumping out of my skin? Probably not. Well, let me say it this way, Scott. One of the biggest misunderstandings people have about this particular class of problems is that if only I had some magic 3 or 4 instructions, life would be much better. Sorry to disappoint people who are in the audience, but there's no such magic instructions. In fact, the ISA is an utter detail to this problem. What is important in solving this problem is the macro architecture, not the micro architecture of which instructions you implement. Now, we chose MIPS64 not because of its ISA. We chose it because of the implementation that they have, which is a simultaneous multi-threaded implementation, which is far and away the best implementation in terms of fine-grained context switching. Much, much better than anything else out there. So let's not fixate on what is the ISA. Compilers were invented, 55 years ago? People are still worried about, okay, what's exact instructions that I have? Please, let's get beyond that. So I think the question here is not what ISA, but does your solution solve the biggest problems in data centers? And what I'd like to close with, because I think we're coming to the end of it, is what's the economic price performance delta that your solution makes? We will stand behind the following thing, that the DPU will make a difference anywhere between 2x and 10x in data centers, as long as they're using scale-out techniques.
Okay, well, Pradeep, we actually are going to run till 10 after, so we still have a little bit of time to go.
Oh, excellent.
And Michael, you're on the ARM side of the fence, I believe, buddy. So what are your thoughts?
Yeah. Well, I agree with Vipin. It's a matter of ecosystem and ability to provide a platform for people to develop. We are not putting arms on the data path, so this performance consideration that Pradeep was talking about were not quite relevant for our case. The key is the ecosystem and the platform for as many developers as it could be possible to so making software guys' life easier to create value of this device.
Thanks, Michael. Now, Andy is a software guy here, you know, and another ARM platform. How do you fit into Michael and Pradeep's?
100% agreement. I mean, that's absolutely why ARM was the choice. The ecosystem's there. I mean, what's really impressive and amazing about ARM is there are enough distributions out there that if you're going to run Linux, for example, and you want to move applications, maybe even applications today that are you know, going to be relevant in the container space, and you want to run those directly on your NIC to save the time that you were spending on your server cores doing things, the transition to ARM is trivial. There's nothing like getting new software, whether it's data plane software or simply control plane software that's managing a hardware data plane, which is the same case for us, just like Michael referenced. There's really, to me, there's not a better choice. So I'm super happy that that's what's on the Broadcom device, and I'm sure other folks that want to leverage the same openness and the same opportunity to have users control their own destiny feel the same way.
Okay, thanks. Appreciate that, Andy. Now, Gordon, you're like the lone guy, since we don't have Intel to poke at today. You're the lone FPGA guy on the panel, you know, and I know you have ARM in the mix. So why don't you give us a few seconds on that?
Yeah, I actually designed an architecture with 100,000 RISC-V cores, but then I had to use an FPGA instead because I work for Xilinx. So yeah, seriously though, obviously we have programmable logic, but there's a lot of other things floating around the programmable logic. And, you know, as a global strategy, Xilinx has ARM cores, or some numbers of ARM cores embedded, you know, in the programmable logic to kind of help out, as I put it. You know, when I joined Xilinx, it was PowerPC cores, but now we're completely ARM cores. But yeah, you know, obviously for the main heavy lifting that's going on, you know, in our SmartNIC architecture, we're looking to the programmable logic and, you know, other hardened function units that help out, like a crypto unit, for example. And then the ARM cores are really there, you know, to help out in emergencies and deal with emergencies. So yeah, well, obviously we're FPGA based, and it's a lonely life here on the panel, but hopefully by the end of it, I'll persuaded you all to use FPGAs.
There you go. I'm going to shift gears and go quite a different direction. I didn't see this come up on Slack, but honestly, it's been itching at me for a week or two now. You'll all probably find out why in 2 or 3 weeks.
Scott, may I make a remark on the previous set of questions?
Sure, go ahead.
And you know, it's curious to me that everyone has acknowledged that, you know, the real problem is in the data path. And yet people keep jumping onto, okay, I need ARM cores inside. Well, clearly those ARM cores are not doing data path functions. They must be doing control plane functions or management functions. Well, I can tell you that x86 probably has a richer ecosystem than ARM. I think people will acknowledge that. You can run control plane perfectly well on x86. So, you know, maybe we can ask our panelists that question. Why does the control plane need to be embedded inside the chip?
Yeah, I'd like to take that one, Pradeep.
Sure.
It's a very good.
I know the answer, by the way, but I just want to point out the disconnect here, because the main problem is data path. It's not a control plane.
Correct.
Yeah,
So yes, yeah. So data path is not an ARM clearly, which is what I think some of the folks also said that. So
Thank you.
So data path is not an ARM. That's very clear. Having said that, on ARM, what you're going to run is like, is my gRPC lib compilable on it? And I don't want to use Go on the ARM core and all that. So there is that aspect of things that makes it super easy to just go with that. But I will also try to touch upon your point as to why not Intel? I mean, yes, it's absolutely the most generic Intel or AMD. Those are the most generic processors. And I know you know the answer to this too, is that, you want it in a single die. First of all, you don't want this to be hopping around the wires and that kills the performance. But most importantly, the amount of tango that you can achieve between, let's say, ARM processor and possibly data path pipelines. And I'll give that example again, like, can we do 1 million instructions per second with one ARM core? Can we do that? Really? I can't do that with one Intel core, forget one ARM core. So clearly not. The kind of, innovation I could do by subsuming the ARM subsystem into my die is tremendous. And that's why it cannot be on Intel. And of course, it gives birth to use cases like bare metal as a service and all that, which is not even possible if you just throw a big Intel on the card. Power envelope will throw off the charts. If I want 25 watt to process 100 gig, no way. I think I can throw a general purpose processor there.
Okay. Does anybody else want to chime in on the whole data path versus control plane path and ARM cores?
Yeah, I can basically agree with Vipin. We don't have as tight interaction between ARMs and the data paths as probably Pensando has. But the key thing here is that if you want to segregate computing of domains of application tier and infrastructure tier, then you need another computer. Okay, you could put x86 and not ARM if it would be practical. And the only practical thing to do is ARM today, so that's why ARM.
Okay. Andy or Gordon, either one of you guys want to chime in? And
I mean, I think the air gap example is a perfect one. I mean, I think this is one of the main reasons the bare metal use case is extremely popular, and not just for people who want to provide necessarily that service to someone else. It's actually gaining a lot of popularity within data centers that are only used by people at the same company. So I think it isn't just about, I mean, if it was just about taking some control plane app and moving it down, yeah, that's not super practical, but that's the inception, that's the beginning. And what you start to see when people start to do this is they realize, oh, wait a minute, I can move this there, I can move that there. And pretty soon they're realizing that, again, as I sort of hinted at earlier, mentioned earlier, they can return their x86 cores to useful work, because, while you might think that it's, super easy to just run those apps on your standard server as well, and it's not hard, they're still going to consume resources. And for my money, I'd rather have those resources be consumed on a device and provide a more predictable use case for my server workloads.
Yeah, in my world, there's a very purist idea, the data planes and programmable logic and hardware, and the control planes in the ARM. But as people might know, we have something of a programmability gap, in terms of just having software-like functions you want to have close to the programmable logic. So you're actually having some ARM cores, next to it, you're within reason, not for like handling every packet or anything like that. It is actually useful, having some actual processors there, you're on chip, alongside the programmable logic, just to get that element of programmability.
Okay. Thanks, Gordon. I'm going to go to a different approach. Some people have kind of hinted at this. We've kind of talked about it or around it. Programmability, obviously, is the key differentiator between SmartNICs and your generic run-of-the-mill NIC, or, programmable NICs. Broadcom has actually made SDKs available for their Stingray platform. How do you each feel about exposing SDK or producing an SDK, releasing it, making it available so that third parties and even, God forbid, end users could program the NICs themselves? Obviously this support opens up a Pandora's box for support. So, what's your company's position on end user or even third party programmability outside your company? Let's
Yeah.
go ahead.
Yeah, we are all for it. We provide SDK, and we work with actually with the ecosystem and the third parties to enable them to host their services on our NICs. So.
Okay, let's go to Andy. What do you think as a software guy?
Yeah, same. I mean, you know, I think one of the best things that we have is that we've done a lot of outreach and had a lot of universities that will take our NICs and use them for research purposes. And other people on this panel have had their NICs do the same thing. And one of the great things about that is that we give them the hardware, we point them towards an SDK or some software, and they disappear. And months later, something is produced that solves the new problem or allows them to do some research on an area and moves them further down the path towards solving a problem. And this is the beauty of this. Like, I don't feel like, within my group at Broadcom, there's a need to feel like we have to tightly control everything that everybody does on the platform. If that's the case, you're kind of, in my opinion, as a software person, doing it wrong. You've got to allow people to put what they want on their devices. And as you begin to think about the expansion of these type of devices throughout networks, I would not want to be a person that felt suddenly limited by what was available on the platform. I would want to do what I want to do, but it might be my open sourceness at heart. So.
Well, you're an open sorcerer. Vipin, where do you fall on this?
Yeah. No, I think I write code, so I'm a software engineer too. And I think that, things are difficult with the way SDK looks like. We need to make it easier. We need to make it like, can I have a gRPC APIs that can program my VPCs and security groups, and I'll just specify a JSON struct into it. That's the beauty of a SmartNIC, where there is enough processing element that you can start to provide simplified user interface to the user. Now you will say that, oh, this is very opinionated. Not really. I mean, we also allow people to define their own APIs, which is why, you define your pipeline, you define your API, if that's what you want. So SDK is not a fixed function for us. We allow people to write and define their own SDK if they want to, but for those who don't want to, just consume high-level gRPC APIs, and they can get going much, much faster rather than dealing with, still lower level constructs. Even if I'm talking about like managing some of the tables and all that, it's too low level for people who want to get going much faster. Why can't I provide like a pipeline for BNG use case and one for VNF use cases, 5G use case, and say like, here is a pipeline I coded, here are gRPC APIs, go have fun. If you want to change it, here's the P4 code, maybe open source that P4 code, they can go and modify that P4 code and change those APIs. So I sense that the approach that we are taking is, for people who want to consume APIs, keep it even simpler than what they are used to consuming. This will allow people to directly control these things from over the network without even having to link anything on the device. But for people who want to own it and define it, yes, allow them to define their SDK instead of like fixing them with some form of SDK that you want to prescribe. So that's the way we are looking at it. And yes, of course, this means you have to put in rigor to build that data path pipeline with compilers and all that. And that's exactly what we have invested in.
Pradeep, how do you fall on this one?
So, I like the way Vipin put it, because we have a similar philosophy, which is that, first of all, we will absolutely provide APIs that will allow people to make the best use of our device. I also believe that the number of people who will write embedded code, I don't mean low-level language, I mean code that runs on this device, will not be the same number of people who program x86, for example. So because of that, we have complete stacks for network, storage, security, virtualization, and analytics. And what we do is we make these stacks available through REST APIs. And these REST APIs will be invoked over the network. So for example, you should be able to perform computations at a much higher level than low-level functions inside the device. So programmability, which we call the ability, it's a big word, call it the ability to do things quickly and flexibly. We absolutely are 100% in support of that.
Excellent. Gordon, I think I know where you fall on this one, seeing as what Xilinx does, but why don't you take two seconds and let everybody know what you think.
Yeah. Well, since Vipin came out of the closet, I'm also a software guy, so you're not alone, Andy. But I think Xilinx is known as the programmable company. So in extremis, people can reprogram their hardware and go in under our SmartNIC and mess around at that level. But obviously, with the kind of SmartNIC overlay, if you like, that's kind of protecting people from the misery of using programmable logic. And we've really taken the lead in the P4 movement. In fact, since the beginning, when it first started, it looked like it might just be a sneaky configuration language for what became barefoot switch chips. But we embraced it very early on, and you have our P4 to Verilog compiler. So we actually generate hardware which corresponds to P4 programs and then put it in programmable logic. So in the actual real Xilinx SmartNIC, in fact, the main functions are implemented using P4 inside Xilinx and mapped onto programmable logic, and that comes as an offering. But then there's plugins where people can add in P4 functions into that pipeline. So we're really committed to exposing the programmability, of being not just going in at the programmable hardware level, which is the ultimate escape route to make things work, but actually at the level where networking people might think.
Excellent, thanks, Gordon. I'm going to take this programmability one step further. I was hoping that other people would ask this on Slack, but it hasn't happened. Given the battle that's taking place right now between Epic and Apple and Google, and they're all fighting over the App Store taxes, right? A number of us believe that in order for the SmartNICs to really make a dent, it would be awesome to have an App Store out there to really enable a third-party ecosystem and expose revenue to other folks and drive the demand for these NICs. What are your thoughts about an app store for NICs, especially your particular breed of or intelligent programmable NIC? Let's see. Let's go with Michael.
The app store for applications or services that can run on our NIC.
Correct.
Absolutely. I mean, it's the matter of how do we organize it and how it gets organized. But as I mentioned before, we are working with the ecosystem to have to enable third-party services to be hosted on our NICs.
So you're a big fan of SmartNICs? Excuse me, of an app store for SmartNICs.
Yeah, I mean, for me, App Store is some a repository where you can go and download certified containerizable whatever application services that can run safely on your devices.
I agree. Vipin, I see you smiling. What are your thoughts?
No, I think I'm smiling because, I think we have thought a lot about this problem. And let's go back to the fundamental question on why SmartNICs existed, because the data path had to be really going on steroids and programmable. So assuming that people want the App Store, I think it is a little bit far out there, and having probably built a real good, fully functioning ecosystem around SmartNIC at Pensando, where you can not just implement, like manage these cards, but also implement these services. And we have written programs that are sufficiently managed at a cluster level, end to end, while multiple of them turn on together. I can say that, if at all we go that route, and we are a little far from there, the reason is because we are working in the P4 community to standardize the architecture whereby people can come and contribute those applications. Where are you going to contribute these data path applications? Because ultimately the reason people are flocking to SmartNICs, let's all keep in mind, is not to just run some thing which is running on x86 to run on the ARM core or on the processors on the card, but it is what they really want is that I want a custom data paths to be running on my SmartNIC, which means you have to have a language for data path. And what's that language? And that language, according to us, is P4. And we have heavily invested in that, of course. But now you have to have an architecture, which we are driving in the community to define what we call PNA, which is Portable NIC Architecture. Once you have that architecture defined, then you need composability on top of it. And then people will have those applications. So we are very much believing that there'll be users who will run applications on this. And we don't think that we're going to write all the applications on our card. Otherwise, we wouldn't have built all the compilers and all these data path flexibility that we wanted. That was not the goal. The goal is certainly that other people should contribute to that. But we are a little bit far from there. If you especially try to think of an application as not just running on the card, but it's running across the fabric, what implication it has if I impose a policy on the incoming card and the outgoing card, how can I really deal with this? How do these programs know each other? So you have a component which is working at a fabric level, you have a component which is working at the card level, but most importantly, you need the standard open organization that can deal with defining the architecture where people can start writing those applications. And so that would be one way of doing it, at least. I'm sure there are other ways.
Pradeep, you mentioned that you guys have a RESTful API into your architecture. Are you a fan of supporting an app store that provides apps for Fungible's platform?
We absolutely are, Scott. But you know, I would suggest to you that we are very early in the game here. What I mean by that is that you can see with the diversity on this panel that there are many approaches people are taking, different approaches we're taking to solving the problem at hand. And while there is not an industry consensus on what that approach is, I think talking about an app store may be premature, just in my opinion. But I think in the long term, once this particular kind of computation is a recognized industry need, and there's also a more or less a de facto agreement about what the right architecture is. Look, for general purpose CPUs, it took the industry 3 decades before we actually got to a consensus of what's the right architecture for microprocessors. We're talking about, you know, being only 3-4 years into this. So I think talking about an app store is a little bit premature, but I think in the long term, absolutely something like that will happen. And we are in full agreement to do it.
I think, you know, things moving faster. It took 4 decades for CPUs. It took maybe less than 1 decade for smartphones.
Yeah,
so
yeah.
maybe it will take just a year for SmartNICs.
Well, I think that's being rather optimistic because please recognize that you know, there's not general consensus on what is special about these computations. One doesn't invent, you know, it's easy to write a PHP or a Python program and make an app, but it's much harder to come up with a grounds up architecture that addresses a class of computations that has just emerged within the last decade. So that's the point I'm trying to make. I don't agree that all of a sudden we're going at, we can invent things in 1 year. No, sorry.
Understood. Now, of course, Gordon, you know where Xilinx stands on app stores, right?
Well, I should have looked it up before I joined the call, but not being a marketing guy myself. But yeah, I think in the previous question, I mentioned plugins. You know, we're thinking of, you know, the architecture that has some basic, you know, SmartNIC functions are built in, and then you can plug in, for example, things written in P4. And in fact, you know, we're also working along with Pensando and others on this P4 PNA portable NIC architecture to try and work out what's portable across NICs. But I think that, you know, one reason to head towards an app store is, you know, when we talk about programmability of SmartNICs, it's probably still going to be a hard programming problem. You know, the previous years of NPU experience showed that, you know, in theory, you know, NPUs were programmable, but only for specialists. You know, GPUs have their challenges in that department too. Yep. And of course, FPGAs, so sometimes not the easiest things to program. So I think, you know, having an app store concept, you know, where people can get apps and plug them into the architecture, it's not your first level experience as you're programming up things yourself, is going to be very important. So I certainly see, you know, having kind of open-ended SmartNIC architectures and some app store notion is going to be very important. But, you know, as as Pradeep says, it's early days, but we can hypothesize, I think, at the moment that this would make sense.
Okay, thanks, Gordon. Tying into that, I'm actually going to pull a question off of Zoom's.
Ooh, do I get to answer? Hold on.
No, you're a software guy, Andy. We don't care.
Throw it to you next, Andy. This one ties into the GPUs. And they were asking, what if we were able to directly connect disaggregated accelerators, GPUs, FPGAs, whatever, and NVMe storage devices to CPUs as if locally attached via direct optical fabric, blah, blah, blah. I'm thinking that, but also coupled more with like C6, CXL, the new protocols that are starting to emerge on top of PCIe 5. And, since Michael's over there checking the smartphone, I figured I'd throw it to him and catch him off guard. Did you get that one, Michael?
Yes, I wanted to start. Yeah, I actually saw this question here. Well, the point is that if we could get along without any disaggregation and just put all the data center, which is like a hangar of airplanes, to a single PC box, then I think our life would be different. And the reason we do this disaggregation is because the balance between different resources for different applications is very different. And just piling it all together, it will probably hit some limitations of the laws of physics. And also, if even ignoring that, it would probably not be a very efficient machine.
Okay. Andy, you look like you're chomping at the bit there to chime in. What are your thoughts from a software guy point of view?
Sorry, I should come off mute. Yeah, common problem. Yeah, I think, I was, kind of jokingly chomping at the bit about the App Store thing. No surprise I'm in favor of that, especially in a case where, you could run, we look at the success of things like smartphones. When you take to that example, the power isn't the phone itself, the power is the apps. So, when you can enable an ecosystem, people to make products, make money, whatever on top of your platform is super important. From a disaggregation standpoint, I think there's obviously, some significant advantages. If you can, when we talk about the ability to have hardware sort of get your general purpose cores out of the way, I think in that case, disaggregation and being able to connect all sorts of different hardware directly to a device is extremely powerful. And I think there's, I suspect we'll sort of ebb and flow between, some spots will see that a disaggregated play like that is really important, and other spots will see that they want things more tightly coupled. I think for me, one of the hardest things is that I feel like over time, the industry has gotten to the point where there aren't as many single solutions that work for everybody. And so I think pigeonholing people into one or another, or thinking that everyone definitely wants to do this one thing is hard. It makes it challenging, but makes it fun too, because there's always something different happening.
Gotcha. Vipin, what are you thinking about C6, CXL? What's Pensando's
so yeah, no, I think it has a lot of promise, and I want to make a high level comment first, which is that it's usually like those horses that are running parallelly, and how much are they decoupled? Like, for example, if underlying technology behind processor technology and the interconnects and the PCI fabric and the networking and the storage is similar, they will roughly move at the same pace. Maybe one precedes other for a little while, and then it supersedes back again. As long as the underlying fundamental underlying technology, what I mean by that is really the processor technology, or just the gates and those kind of things. As long as those are common and those are similar signatures, it will be, disaggregation or decoupling these things will not be super meaningful, because, I will align myself to one clock and then, go with a thing, and then, just purge that out when I'm done with it. And that's the there was a promise that, this whole thing was, I believe desegregation is not new. I've been looking at that back in Cisco UCS days since 2006-ish or so. I firmly believe that, it is really the innovation speed at which all these other things are going on that allows people to think like, oh no, I cannot move as fast as this thing, so I have to retain this one but change something else. And that's when I think you start thinking about these as discrete components. And the truth lies in the fact that, majority, I would say 90% of servers that are used today are like, standalone rack servers. And sure, there is some promise to those things for some other cases, but a PCI technology that enables you to do that is going to be, caught up with subsequent, innovations on the other hand, where it'll catch up with that as well. So can we consume all that naturally? If we can, then we'll be where we are.
Thanks, Vipin. Pradeep, how about a minute on CXL C6?
Scott, this one question is actually the first question on interconnects, given the title of our panel. But I'll reflect on it in this way. I think there are two different types of interconnects. One which is interconnects that provide a memory model, where the primitives are read and write. PCI is an example of that. CXL is an example of that. And then the other model is a network model. And to some extent, the memory model guys are scale up in nature. Okay, they're trying to build a bigger, faster single thing. The network model, on the other hand, is completely different. It's scale out. I happen to have worked on memory models a long, long time ago. And all those large-scale multiprocessors have gone the way of the dodo bird. And they went the way of the dodo bird because the cycle times of building these things are long and complex. And having worked on both sides now, the network side and the memory side, I believe that trying to build very large single things which are tightly coupled with a memory model is probably not a great idea because you're going against laws of physics. On the other hand, the network model has proven to be very resilient because you can build hundreds of thousands of servers, connect them together with a standard-based network, and provide the kinds of capabilities that you would in a single large computer. And I think disaggregation is here to stay. Scale out is here to stay. I think that the network model is the one that is going to win out at the end. You will have people building C6, Gen Z, CXL based things, but they will be generally contained within a system, maximum at the level of a single rack, not more.
Okay. I'm going to do one last quick yes/no question, and it comes from one of the other guys on Slack. If someone was to come up with an industry standard API or protocol for publishing software for an app store, is that something that your company might likely get behind? Because obviously we've got on this call 5 different approaches to cracking the problem, and developers don't like taking their code and having to write it or rewrite it 5 different times. So yes or no, would you be for a standardized way of promoting apps in an app store to your platform?
Absolutely, I would be, assuming it's at the right level of abstraction, high enough.
Okay.
Lots of machine language.
Vipin, your thoughts?
Well, I think there's a joke, and I'll give you a quick joke, and then I'll give you my answer. The joke is that only because current standards are not good, I have to build a better one. And I think coming to Pradeep's point also is like, what is that API? If you can agree to that, and so we need to first discuss those problems and do that. So why would I say no? Absolutely, we are so flexible in defining and adapting ourselves to most of the things that may be out in the future, like 2 years, 4 years down the road. So answer is definitely yes. But I think it requires us to spend incredible amount of time to get to that that agreement.
Okay, Gordon, I missed you on the last one, buddy. I didn't forget you. Yes, no. What do you think on this?
I'd say yes. And the encouraging thing I'm taking away from this panel is, we've got 5 different approaches here, but the number of common things we have, just following the discussion, is way greater than the differences. So that gives me hope, for having some kind of, cross SmartNIC, if we can say SmartNIC now, initiatives like that. So yes.
Andy.
Oh, yeah. I mean,
Basically,
basically
I'm going to say yes. Of course,
basically doing it already with Linux. I mean, that's the answer.
There you go, Michael.
Yes.
Yes. Okay. Now we're coming down to the very hairy end.
Answer is actually, there's 5 people here, so I think we are so wholeheartedly agree. So we would come up with probably 5 different standards. So we are all agreeing.
Okay. Artem, give me one more second, buddy. Everybody, you're allowed to say one string. SmartNIC, DPU, or IPU. I'm going to start with Michael.
So what's the question? What name would I use for this programmable NIC?
Yep.
Well, I'm not marketing guy.
Yeah, okay. You're going to CTO forever.
DPU sounds great, but.
DPU. Yeah. Okay, Andy?
I'm going to go with SmartNIC.
SmartNIC. Vipin?
I think there should be domain-specific data processing unit, and so I'll go with
domain-specific data. Okay, so he's going with a whole different one.
You get a lollipop.
No, I mean, it has to be domain-specific, and DPU captures that. It's a data processing unit. And so, I mean, we call it distributed services card, but like I said, I'm not a marketing guy either, so I'll pick something that captures the essence of it. I think DPU does a better job than SmartNIC.
Pradeep, we know you're going to say DPU, buddy.
Yeah, well, we put our money where our mouth is. It's DPU for us.
Gordon?
Well, so the DPU is a registered trademark, so we'd better stick with SmartNIC at Xilinx probably.
I don't know if it's registered trademark or not. I've seen 2 or 3 different folks on this panel actually use it in their marketing manager. Okay, Artem, I think that's pretty much it, right?
Thank you very much.
Hey, Scott, thank you so much for organizing this and for inviting me on the panel. And this was really a rich discussion. Fantastic.
Thanks, guys.
Thanks for co-panelists.
Thanks, Scott.
Really appreciate it. Thanks.
Thank you.
Thank you.
Okay.
All right.